This is an overview about this question. This video is focused on batteries. Question A asks to differentiate two important terms related to a battery. Question B shows a diagram with two battery sources and its internal resistance. Kirchhoff's second law is applying the circuit to calculate the current flowing. Then this current is applied to calculate the power transformed by the battery B and the energy lost due to the combined resistance. The definition of electric motive force, abbreviation is EMF. EMF transfers chemical energy to electrical energy. And the internal resistance of a battery is the resistance of the cell or battery, causing energy loss, like heat. Now, this circuit shows two batteries, A and B, and a resistor R connected in series. If they are connected in series, so the current flowing through the circuit is the same for all of them. So battery A has an EMF of 3 volts and an internal resistance of 0.1 ohms. Battery B has a EMF of 12 volts and an internal resistance of 0.2 ohms. The resistor R has a resistance of 3.3 ohms. Apply Kirchhoff's second law to calculate the current in this circuit. I'm going to pause this video to explain the connection of this battery here. We have two symbols for battery. So let's see how this works. This is a single battery. So this is the positive sign and this is the negative one. And this battery is 1.5 volts. Now these two batteries, they are connected in series. This is the positive and the negative of this battery. And this is the positive and this is the negative of this battery. So both, they are connected in series. Before applying Kirchhoff's second law, we need to determine the direction of our loop. The current flowing in the circuit is the same because they are all connected in series. The direction of my loop is from the higher battery to the lower battery, so in this direction. The general rule is that if the current flowing in the circuit or in the loop has the same direction of the path of a loop that I choose the direction, so then the PD is positive. To solve this question for the current using Kirchhoff's second law, we need to determine the EMFs. So here we have, this is the path of my loop. So now I'm going to, this is the positive and this is the negative. And the same here. So, and these will be my negative and then my positive. They are in series, so it will not matter. So they are kind of combined. So this is kind of just one. This is the negative and this is the positive. So following my loop, so positive, negative, so that is my negative battery, and this one will be my positive battery because it's going from negative to positive. So when a battery goes from the negative to positive as a direction of my loop, so this EMF is positive. So this one here will be 12 volts. And the second EMF will be this one, which is from positive to negative, so minus 3 volts is equal to, now let's look our three resistance. There were three resistors we have here, three resistance. So because the current is flowing this way, is the same direction of my loop, so that will be the current I times 3.3 ohms. Now let's look at the next one. So this is my current is flowing in this direction through this resistor. So then I have plus I, and the resistance on this battery A is 0.1 ohms. And the next one is my current is flowing this way. So it's the same direction of my path, so plus 0.2 I. So here doesn't matter the order, if you have the resistance first and the current last, will not matter. Since the current is the same, so we just need to add 3.3 plus 0.1 plus 0.2 is 3.6. So this is symbol for voltage. So it will be the I is 9 volts divided by 3.6 ohms. So I have 2.5 amps. The next question is asking the power transformed by the battery B. So the battery B, which is this, the voltage is 12 volts, and the current flowing here is the same current that is flowing the entire circuit, which is 2.5. So I'm using the formula for Ohm's law. So the power is equal to the voltage times current. So the voltage is 12, the current is 2.5, and the power transformed by battery B is 30 watts. Let me pause this video to review the concept about power. So power by definition is the rate of energy transfer. Rate is anything over time. So is the energy over time. So the unit for power by definition is joules over second for the SI units, or joules times the inverse of a second. Now, this unit is also known as watts. So we can use this here. You can use just this unit, but is most common using watts. So joules per second is the same as watts. So following the sequence of this problem that we calculated the current, we are going to use this current on our next question. So this question is asking the energy lost per second, but this is power, energy lost per second in the resistor R and the internal resistances of each battery. So in this case, we can use the formula for power instead and incorporate the current that we calculate, which was 2.5 amps, flowing in that circuit, and calculate the total resistance. Since all resistors, they are in series, so we can add them. So to solve this problem, P is equal, I is 2.5 square, and each resistor is 3.3 plus 0.1 plus 0.2. So when you plug in your calculator, the answer is 22.5 joules per second. So that is the energy loss per second. Last question. This circuit may be used to store energy in battery A. Suggest how your answers in B support this statement. We can say the power supply by the battery B, which is 30 watts, is greater than the energy lost in the circuit, which is 22.5 watts.